Okay, let's introduce the semantics with a simple example. The first thing we have to do is decide what we're going to do with our semantics. We can do many things. For example, we could see whether the program is correct. This is called verification. Or we could see whether the program is well designed, or we could explain the program, or we could calculate time and memory utilization, or we could explain garbage collection, how the program manages memory. But in this example, let's concentrate on the first goal, the simplest and most important goal of semantics, which is correctness. A program is correct when it does what we want it to do. How can we be sure of that? Well, we have the program specification, okay, and we have the language semantics. So we have to prove that the program satisfies the specification using the language semantics. So the language semantics is the means for doing this proof. So we have three pillars. We have what we want is the specification, what we have is the program, and then we have the semantics which connects the two. The semantics is the bridge. With the semantics, we connect what we want and what we have. So with the semantics, we can prove that our program is satisfying our specification. So here's an example, simple example program. Let's use a factorial. So the specification is a purely mathematical construct. 0 factorial is 1, and n factorial is n times n minus 1 factorial when n is greater than 0. The program is a pure programming language construct. Fun fact n, if n equals 0, then 1, else n times fact n minus 1, and end. So the semantics now is going to connect these two. So we're now going to connect them, and we're going to connect them to make a proof. We have a proof. We want to make a proof. So we have a recursive function, factorial. So the proof has to use mathematical induction. Mathematical induction is the technique that's used for recursive entities. So a recursive function calculates on a recursive data structure. In this case, it's integers, positive integers starting from 0. So there's a base case, and then there's a general case. So we first want to show correctness for the base case. This case will be 0 in our example. And then we want to show that if the program is correct for a particular general case, that it'll be true for the next case. So in our case, this is going to be integers. The base case is going to be 0, and the general case will go from n to n plus 1. In other programs, it could be 1, for example, or other kinds of small integers, but it's always going to have this general structure. If you have a program with lists, you also have a similar kind of structure. The base case will very often be nil or a small list, and then you have a general case, which is some list leading to a list of one more element. But for our example, we're going to look at integers. So here's our proof. So here's what we have to prove. We must show that calling factorial n will calculate n factorial according to the specification. So our proof has two cases, a base case and general case. So the base case, n equals 0. The specification says 0 factorial is equal to 1. Now what does the program say? The execution of factorial 0, the program, using the semantics, gives factorial 0 equal 1. We'll see in a moment how we can do that, show that. It's 1, so it's correct. The general case now, from n minus 1 to n, the specification says n factorial is n times n minus 1 factorial. So what we're going to do is we're going to execute factorial n using the semantics. This gives factorial n is equal to n times factorial n minus 1. We can assume through the induction hypothesis that factorial n minus 1 is n minus 1 factorial. We assume that the language correctly implements the multiplication operator, and therefore we can show that factorial n is n times n minus 1 factorial is equal to n factorial. So we've proven things correct. Now this is our proof we have just now to show one piece, the violet. What does it mean exactly to use the semantics? How can we show that factorial 0 gives 1 using semantics? How can we show that factorial n gives n times n minus 1 factorial using the semantics? So that's what we're going to do now. We're going to show how to execute a program using the semantics. So to do that, we have to follow 2 steps. The first step is to translate the program into the kernel language. So the kernel language is a simple language that contains all the essential concepts of a paradigm. It's simple because that means later when we do the execution, it will be simple. And all programs in the practical language can be translated into the kernel language. So what we're going to do then is translate the definition of fact into the kernel language. The second step then, after this, is to execute the translated program on the abstract machine. So the abstract machine is a simplified computer. It's not a complicated computer like an Intel processor, a Core i5, whatever. No, it's a simplified computer with a completely precise mathematical definition. So what we're going to do is we're going to execute our call, for example, factorial 0, and this becomes a procedure because it's kernel language. We will execute this on the abstract machine. And then we will be able to fill in the blank in our proof. So the first thing to do is to translate the definition of factorial into kernel language. So here it is. So the function has become a procedure. We've introduced identifiers. The R here, which is the result of the function, becomes an argument to the procedure. Also in the if statement, an if in the kernel language must use an identifier as an argument, cannot use an expression, so we have to introduce this identifier b. Also, in order to do the local calculation n times factorial n minus 1, we have to introduce 2 identifiers, n1 and r1. We first do n1 as n minus 1, and then after calling factorial giving us r1, we do r is equal to n times r1. So this gives us the factorial in kernel language. We've only used instructions in the kernel language, and all intermediate results are visible. Nothing is hidden in the execution. So now we have this kernel language definition. We can execute it using the semantics. So we have to do factorial 0 and factorial n. Let's look first at the function called factorial 0. In fact, we have to execute a procedure call because we're in kernel language, and let me give identifiers here, but the n argument will be equal to 0. In order to execute this, we need a memory, sigma, and an environment, e. We need a memory to calculate on. We've seen already what the memory looks like. We've already seen the concept environment. So in our case here, the memory sigma contains 3 things. It contains the definition of factorial. So this is a fact variable bound to this procedure. Notice we have the code of the procedure, and we have the contextual environment, which contains just factorial because it's a recursive function. We also have the n argument and the r result, which is unbound. The second part is the environment. We have 3 things, fact, n, and r, in fact, which are just the 3 identifiers in our call. Okay, now we can finally execute. So what we're actually going to execute is this, is the instruction combined with an environment and a memory. So that is what we're going to execute. So, okay, so to execute a procedure call, what we do is we replace it by the procedure body. So the instruction here, which is the procedure call, is replaced by this, which is the procedure body. I am not giving everything. Notice I've put ... here for the recursive calculation, but this is the procedure body. And notice that this environment here is the environment that we will use during the procedure body. This environment contains the arguments n and r, and the contextual environment, fact. And we also, of course, have the memory, which is just sigma. So now we have just done the first step of our execution on the abstract machine. Let's now do the second step. So the second step is we go farther. We have this local instruction, which is the body of our procedure. We have to execute the local b. What does that do? That does two things. It extends the memory, sigma, with a new variable little b, and it extends the environment with a reference from the identifier b to the variable little b. We can then replace this instruction in the execution by its body, which is the part inside here, b equal n equals 0, and if b then etc. And notice that our environment gets extended here, and our memory also gets extended. So we have then now done our second execution step. And now we continue. Now we have to execute this instruction. The way that works is we will execute the b equal n equals 0, and then the if. So the first one here, b equal n equals 0, will do this comparison and eventually will bind b to true in the memory, and then the if will execute, and since b is true, it will execute the r equal 1 in the abstract machine and bind the r variable to 1. So this completes the execution of factorial 0 in the abstract machine. So we have done the execution in the simplified precise machine. To complete the proof now, we still have to show that the result of factorial n is the same as n times factorial n minus 1. Remember, that was the second case in our inductive proof, the general case. So what we did now is just the base case. So I'll leave that as an exercise. Let's now recapitulate what we've done here. We have started first with the specification and the program of factorial, and we wanted to prove that the specification is satisfied by the program. Since the function factorial is recursive, our proof will use mathematical induction. In this proof, then, mathematically inductive proof, we have a base case and a general case. The base case, we have to prove that factorial 0 gives 1. In the general case, we have to prove that factorial n gives n times factorial n minus 1. That we have done. So we prove both cases, and in order to use the semantics, what we have done is we first translated fact into kernel language, and the second step is then we execute it on the abstract machine. And this completes the proof.